continue today's seminar by some presentation about risk-based demonstrability requirements. That is a subject that I already addressed in the first part, but we'll go now here in more details. And this is more or less the essence of the project goals that it was an EU-funded project that we finished 3 years ago, and led to some proposal to IMO regarding the demonstrability requirements. So you see a list of contents of this presentation in this slide, and I will explain you here how we set up this risk assessment framework, and finally also after doing some studies on assembly of ships by applying so-called risk control options, then finally we came to propose some requirements for the demonstrability that were based on cost-benefit analysis. So as an introduction, some comments on SOLAS 2009 required index. The required index is something set by regulations, which needs to be exceeded by the attained index of the ship. And this was formulated in SOLAS 2009 by the results of Project HARDER, that was an EU-funded project, harmonization of rules and design rationale, that ended in 2003. And in this project also we participated and partly presented some of this research in the first part of the lecture. Now, the critics at that time on SOLAS 2009 were that there were not enough large passenger ships considered in the sample studied by the HARDER project, and this raised concerns regarding the suitability of the developed standard for large cruise ships, especially among the IMO delegates. Also, the representatives of the cruise ship industry, especially those having large cruise ships, they said that the safety level of the mega cruise ships was higher than that coming out of some application of SOLAS 2009 in terms of demonstrability. That means the survivability of this vessel was higher, and this was not reflected properly in the SOLAS 2009 S-factor formulation, and this needs to be improved. And project goals needed to provide now some research and evidence on this, how to change it. Also, survivability following collision events was addressed, but not probability of grounding and related accidents. The FSA studies on cruise vessels and RoPax ships performed within SAFETO. The SAFETO project was run actually after HARDER, and they concluded, these FSA studies, that we could reduce the risk on human lives, I mean people on board, by increasing the survivability of ships, and this could be done cost effectively. But again, people said, okay, we did some studies, but not enough vessels were studied. This cost effectiveness was under question. And we were asked to study additional ships. And finally, the project goals that ran between 2009 and 2012 had to do some submission to IMO for addressing these concerns. So what we have to consider is that prior to project goals, the studies that were in the SAFETO FSA studies on cruise ships and RoPax ships are in terms of sample of ships and casualty reports are outlined in this graph. We took into account ships of GRT tonnage over 20,000 tons. Then the casualty reports and the fleet at risk was for the period 1990 to 2004. And we used for the analysis of accidents Lloyd's Register Fair Play, LRFP at that time. The FAI explained that in more recent study, also in Golds, we used IHS database that is a further development of LRFP, former LRFP. Lloyd's Register Fair Play, is the acronym for it. For the ROPAC ships, we used ships with GRT over 1,000 tons, casualty reports and fleet at risk for the period 1994 to 2004, and Lloyd's Maritime Investigation Database, not exactly the same like the other one, no? Different source of data. Now, the development of the new R index in Gold's project that was now risk-based and was different from the harder project that was a statistical derivation of the required index. Was based on the outcome of 3 tasks in work package 5 of Project Goals. As you can see, the first task there was the development of standard risk models for collision and groundings of passenger ships. And you see also the partners participating, that was NTUA, coordinating, GL, SRC, here from Strathclyde and DNV, so 2 class societies and 2 universities for working on that. Also, benchmarking against existing results, the same group was participating, and finally, the formulation of the new serviceability requirement was by a group enhanced by shipyards, Maiver, Fincantieri, STX Fincan, STX France, then 3 operators, Carnival, Royal Caribbean, and Caroline, GL is Caroline, MCA, DMA, the 2 flag administrations, MCA from Milan and DMA from Denmark, SRC, NTUA, GL, and DNV. You see, a large group was necessary for making this proposal, because always if you set up requirements, then you need to have a consensus among the participants. And the whole industry and the flags and class societies needed to participate. And as you see, this was coordinated by a shipyard, Maiver. So now let me tell you how we proceeded in that. So we see here this chart is more or less what we follow up in a formal safety assessment. We have a step 0 that is actually some definitions of the problem in hand, then the hazard identification, and then we have a box inside where is the actual risk analysis and what we conducted also in goals. Then having the scenario definition, I mean, what kind of hazards we consider. Then calculate the frequency of accidents and also the consequences, and then options to decrease the frequency. That means the risk control options, how to decrease the frequency and the consequences. And the question of whether the risk is controlled by this kind of measures. If not, then you go back and try with another risk control option. If this is controlled, then you do a cost-benefit analysis to see what you are doing, whether it is cost-effective, and then you come to some end. The cost-benefit evaluation is, as it is described here, is comparable to steps 2, 3, and 4 of the more process. And in the context of Gold's project, the consequences that we evaluated and what we like to reduce were the potential loss of lives, the PLLs. Now, the steps that is first to specify a sample of to build up this kind of risk model. You need to specify the sample, statistical sample of ships that you consider. That means the ship types and the study period. I commented before that already this is something you need carefully to do, especially okay, the ship types is trivial, then in this case robots and cruise ships. But the study period, how you go backwards, it is a question because the older ships you take into account, then maybe you have some obsolete technology that may influence the accidents, and then the sample is not good enough. On the other side, the more recent the study period is, the disadvantage is that then you have less records, less records to analyze. So you need to find the right trade-off between them. Then a second step, you have to determine the fleet at risk. That means the operating fleet in the study period. That is, I explained before. I will come to that back anyway. Then to see the number of accidents during that period and calculate the accident frequencies. Then to develop the high-level event scenarios. That means you need to develop for the collision and grounding the scenario, how this happens, and as a follow-up of the collision or grounding scenario, whether the ship eventually will sink or not, and how many fatalities you have. You build up the risk model or the event in this case. Yeah. And sorry, somehow. Lots of pointer, or what is? I need to step up. Because here I cannot see the pointer. Okay, and then we need to develop these dependent probabilities of the risk model, and I will come to this to explain you that. So regarding the fleet at risk and the casualty reports, that is something Eleftheria explained you in the last lecture, but I will come here with some more specific things. The selection criteria here were in terms of ship types, RoPax, rail, cruise, and pack ships, that means few passenger ships. Gross tonnage was over 1,000 tons. The length over 80 meters, built after 1982, the ships, because we wanted to have ships with relatively new technology. The period we started was between 94 and 2010, 17 years period. We consider that this period is not too old, enough long to have good data. And just pay attention that if you restrict a period or a shorter period, of course you take into account only the accidents taking that period with a fleet at risk. Take a longer period, then you take more accidents to account, but over more ships. It is not so that the results will change significantly. But still, you need carefully select that. Then we took into account only Ajax ships. The Ajax, as you may know, is the International Association of Classification Societies. This is the first league of class societies. Why? Because we didn't like to have underreporting, because we know that other classes outside Ajax, they do not report accidents. So we wanted to be sure that if we have ships of certain class, that the extent possible all reports of casualties should be there, not underreporting. And then a filter was there also that the full number should be less than 0.5, and this ensures that high-speed cars were excluded. So sounds relevant to this regulation. High-speed cars have, for the example, the high-speed code that is different from what we are discussing, including multiple bodies, catamarans, and so on. And then we made out of that two ship categories, cruise ships and RoPax ships, where for the cruise ships we added also the pure passenger ships that are mostly smaller ships. There are some ships without taking cars. And the RoPax ships were RoPax and RoPax Rail, that is also those carrying trains. So now regarding the liability of the casualty reports, and that is something that we discussed already in the presentation of Telefonia, that some records, they were very poor without technical information, so we properly screened that, and to the extent possible, we produce our own database for this analysis. Also, something important is the coding of accidents, serious and non-serious, by IHS. Because very often this was wrongly done, so we needed to look carefully into this. And here you have first the fleet at risk for the period is indicated. Ships built after 82, GT over 999, and the foot number less than 0.5. So you see here the various categories, the number of ships, Ajax and non-Ajax ships, and then in total the ships, if we take the various categories into account. So actually we took this one, Ajax only, Ajax ships only. And here are the fleet at risk. This is the fleet at risk for each ship type for the study period. Noting that we merged this into one group, in two groups actually. And you see that we had for the cruise and attack ships about 2,800 ship years, whereas for the RoPax more than 5,500. That is a more rich sample. Now, how this fleet at risk was calculated, you need to go into IHS database and see at when the ships were used to be delivered. Then you can see how many ships are to be delivered in a specific year, and then consider those in the specific year whether some ships were scrapped or they were total losses in order to be hit. Okay, and then out of this, you can see over the years how the fleet develops. So here's the development of fleet at risk for the study period from 94 to 2010. You see a continuous increase of the fleet at risk, but the reason for this is not that the vessels in total change like that, but here you need to see that we consider here ships built after 82 and not the older ones. That means, okay, in that respect, the more you go, then the more this sample establishes and comes to certain maturity. But clearly we have more RoPax ships than cruise ships. But this is what we take into account per year. Then for every year we look then also into the accidents. Divide by the accident to find the collision grounding frequencies. So here are the reported casualties for the collisions, cruise, parks, RoPax, and rail. Then you see for this period of 17 years, there are in total about 65 casualty records, collisions. And if you divide that with respect to fleet at risk, then you get here these accidental frequencies. that you see it is for the cruise ships 7, 10 to the minus 3. For the ROPAX, it is higher, a little bit higher, 7.78. And here is the respective numbers from the same study that were for another period. And they are slightly different. We see here that for the cruise ships, this increased a little bit, whereas for the ROPAX ships, the frequency decreased, because here is 10 to the minus 2. The same study stopped in 2007, and there was another sampling period. These are the collision statistics per year for 1994 to 2010. That is, with some peaks here in 2007 and 2008 for the ROPAX ships. And here are the annual collision accident frequencies for cruise ships and ROPAX ships. The cruise ships are in the blue diamonds, and the red are the ROPAX ships statistics. So what you can see here is, of course, a spread, very big spread. And the question is how then you calculate average frequencies. In some years you have 0, and some other years you have, okay. Then you need to take average over a certain period. And the averages are here for a 10 years interval. That is a running average. You take a sample for 10 years and then you proceed. Here is for 1994 to 2003, this is the average frequency. Then 95 to 2004, these are the, okay? And we see, of course, that here the frequencies increase the more we come to the more recent data. For the collisions, we have for the ROPAX ships a little bit higher frequencies than for cruise ships. And if you go to the groundings, then things are different. The groundings, the statistics say, and the accident frequencies, that cruise ships have higher frequencies, 1 10 to the minus 2. And ROPAX is almost like the collision accident frequencies, 4.8 10 to the minus 3. And here again are the grounding casualties per year that you may divide with a figure risk to get them the frequencies. And again here, now for the grounding, again the spread, and these are the average, the running average for 10 years period. Here the cruise ships are with higher frequencies. What is evident here is that cruise ships are more prone to be engaged in groundings. So ground is a more important hazard for cruise ships than for ROPAX. And we need to consider that later then also in the risk analysis. But another thing is that between the two ship types, there are some differences in terms of casualty statistics. At the end, however, at the end, the required index for both ship types will be the same. We don't differentiate, have another required index for cruise ships and another required index for ROPAX. It will be the same index. And the reason for this is that in both ships, some people are traveling. And you cannot say, okay, I will accept for the risk for people on cruise ship another risk level than for those traveling with a ROPAX ship. So now a few things about these inventories that we developed. The inventories are a basic element of risk analysis, and you need to figure out in this kind of analysis out of a collision what can happen and what is the probability of every step in this procedure that something happens. At first, here we have a collision. The collision, we could see it is something in the range of 10 to the minus 3. Okay? What that means, you can have something like 4, 5, 10 to the minus 3 collisions per ship year. After you have these statistics, then you can come here to other probabilities, namely, what is the probability that, okay, we have a collision, what is the probability that the ship is stuck or the ship is striking, because then collision has 2 participants. If you don't have better statistics, you assume a 50-50 probability. Okay? But in reality, we know that between RoPax ships and cruise ships, there are differences. And some of them, they tend more to strike other ships than to be the struck ship by some other ramming ship. Huh? This you can take into account. And then you have the operational state. In this case, you need to see, according to the statistics, where this accident happens. Does it happen in the open sea? Does it happen in limited waters? What we say limited waters means near ports, but where maybe maneuvering is hindered, but anyway, near the coastline, where some help can come. And finally, the third thing is whether the collision is in terminal areas. That means terminal areas that is within the port. And you have a collision in the port. Of course, the consequences there are much different than if the ship sinks in the open sea. Also, according to statistics, we'll see how these things develop. Then, the sea state. What kind of sea state is likely the ship to have at that location in the open sea, in terminal areas. Then, okay, we have the water ingress, we have the collision in terminal areas in the open sea. What is the likelihood that you have an opening and then flooding? What is the probability for this? Then the sinking. The probability of sinking is actually 1 minus A. This is something you can calculate according to the probabilistic approach. Maybe 20%. It depends how your attention index is. But here you have also to assume that something, whether the sinking velocity, whether the sinking is fast or it is slow, based on statistics, or maybe numerical simulations you can do that on ship types. Here also we have included fire, because in some cases, before, if you have a slow sinking, out of the accident, the collision, some fire may also develop. That is some additional hazard that is needs to play a role. And finally, the consequences, that is evacuation analysis, and then how many people then may be saved out of this. So this is an inventory, a complete inventory for the collision event. And all these branches here need to be populated with probabilities, what we say, dependent probabilities. Dependent because everything depends on things before. And if you have here some probability, 5, 10 to the minus 3, then you need to multiply all these probabilities in order to have the probability of a consequence. All these are multiplicatory probabilities. So for the groundings, the event is similar, but there are some differences. You have the probability of grounding. I explained you how you determine that. Then the question is navigation, and whether the grounding goes powered. That means the ship with power grounded, or there is some blackout of the engine, or maybe some stuck Yeah, non-powered, non-powered grounding is no engine working. That means that the ship was drifting and then it grounded. So you need first to differentiate with respect to this. The second thing is then what kind of seabed you find. So if you ground on a hard rock or a soft bottom, seafloor, because the consequences of course are different. In the second case, if you are on a sandy beach, then it is the beaching that rarely brings flooding to the ship. The ship may stuck, but not going to. But if it grounds on a rock, then in most cases there will be some opening and flooding. Then you have the water ingress, and after the water ingress, the question is whether the ship is staying aground. That means it's stuck on the ground, or if the ship, because if it's stuck on the ground, then it's not going to sink. Yeah? But if it stays afloat, it grounds, and then maybe on some rock like Costa Concordia, then it is free to go afloat, then it may sink. And finally, the consequence again in terms of evacuation of the ship, how quickly this can be done, and what kind of consequence. So then here we have some probabilities in terms of percentage. I mean, here George prepared this, Zarafonitis prepared this. So this is in terms of percentage of, it's not of 10 to the minus so on, but in some collision event, in what percentage of cases some collision event will happen, and what are the consequences. But the interesting part is here, stark and striking. According to statistics, cruise ships, in 62.5% of the cases, cruise ships are going to ram other ships, and in only 37% of the cases will be the stuck ship. For ROPAXes, it's just the opposite, no? 69 and 31. And then whether the ship is en route or in limited waters terminal, then statistics act like that. So collisions will be for cruise ships in 73% in open sea, where the ship is en route, only 4% in terminal areas, and ROPAX ships the same, we didn't have better statistics. And for water ingress, we have for ships in the open sea, in terminal areas, 10% of the cases, or just the opposite. So terminal areas is 73%. Open sea is only 4%. So 4% en route, and water ingress 42% in this case. So if the ship collides in the open sea, then in 42% of the cases, water will ingress the ship. In terminal areas, only in 12% of the cases, because this is some low energy collision and then not likely to get an opening. If the ships collide in terminal areas, they don't have enough energy to penetrate. For the groundings, we see the statistics say that 89% of the cases is powered grounding. That means for whatever reason, with the engine working, the ship is going aground. Only 11% of the cases will be drifting because of brake of the engine. Then in 75% of the cases, the ship is going to hit hard rock, hard ground, and 25% soft. And the water ingress will be 92% in hard ground. In soft ground, there will be no water ingress. And in 38% of the cases, it is assumed that the ship will then, after that, go afloat. That means it may sink out of if you have river flooding. So these probabilities they were implemented in these event trees. This is for collision. And then we have there two cases regarding fatalities. After the ship, we assume that the ship was sinking. When you come here, then the consequence of sinking, according to model A, was that we have 100% fatalities. That was either thinking that leads to more severe consequences. So it was promoted by some researchers, especially here from this university. It is the same concept, of course, also followed up in the aviation. But in this case, when the airplane is crashing down, then there is no way to have 100% fatalities. But for a ship, then we applied a second model, model B, in which we assume that we may have fast sinking and slow sinking, and then depending on this, then we assign number of fatalities, some percentage of fatalities. And then we had for fast sinking, for cruise ships, 18% of fatalities. No, sorry. In 18% of the cases, we assume that the ship would fast sink. In that case, 80% fatalities. Slow sinking, 82%. And in that case, 5% fatalities. For the rope action, we assumed a 50-50% case. So slow sinking and fast sinking goes 50-50. And then accordingly, the fatalities were for fast and slow sinking the same as the cruise ships. So this is a model that can be supported also by historical data. I explained to you before the break that, for example, even the Estonia disaster, where that happened in the open sea in the night with heavy weather, still in that accident we had about 80% fatalities, less 75%. So not all people were drowned. So we cannot even under worst conditions we cannot assume that everybody is lost. On the other side, you remember this other Filipino ship. Then that much more people. The percentage of fatalities was much more. So it depends also how quickly the rescue is by notified authorities on the shore. And even Estonia was far away from the shore, but even by that, in the night, there were rescue teams and 137 people were rescued in the Estonia. Anyway, this is something that you can argue for a long time, but there is nothing better, I can assure you. No way in the world you can find some better risk model than this. You can say, maybe you can try to support this in different way, maybe scientifically in order to estimate the time to capsize, to estimate the time to evacuate and see how these two things compare, and have also some simulated data, but something better you cannot do. There will be always some uncertainties in that. Okay, here again, the whole tree populated. I don't need to go into details in this. And this for the collision for cruise ships and ropax ships, and the guiding model for cruise ships and ropax ships. Maybe later, when you see this kind of charts in details, you can study the numbers and try to understand how these were derived. But the principles, how they were derived, I explained it before. It's not that complicated as it appears here. Yeah, at any branch, you need to decide what is the break, what options you have, and between these options, what is the probability that these options come. That is the whole way how to decide here whether it is powered grounding or drift grounding. Okay, then that is what we discuss. And in this case, what is the probability to have soft ground or hard ground? So having now established the probabilities of that the accidents occur and also the consequences, then in order to complete this risk model and calculate the attained indices, we needed to assume something about the so-called P and V factors. The P and V factors are the extent of damages, what is the likely damage extent in terms of length, in terms of height, and penetration. These are described in the P and V factors in SOLAS 2009, and these were not changed in the GHOST project. But what was new in the GHOST project is a new S factor that was proposed by SRC, and this S factor is based on the so-called critical wave height approach. So what is the critical wave height? It corresponds to the sea state at which capsize rate equals 5%. That means at first you calculate some wave height that is maybe imaginary, and then you ensure that only 5% of this wave height will lead to some capsize by your ship in order to have a certain safety level. And at second, the probability of survival of the ship is equal to the probability of exceedance of this critical wave height. So first, you calculate for your ship the critical wave height in terms of some ship parameters, and then you say, okay, now I sail with this ship in this sea state, what is the probability that I exceed this critical wave height? And this is equal to the probability of survival of the ship. The S factor is the probability of the ship surviving a certain collision damage, according to our list approach. And this problem here is reduced to a problem, to the probability of exceeding a certain wave height, that is the critical wave height for your ship. That is the whole concept. Now, after having the S factor and the P factor as I described, then we could calculate the attained index by considering the three loading conditions, the subdivision, draft condition, the partial drop condition, and the light drop condition. That means you consider the various damage scenarios as here, but for the three different drafts, assign weights of 40, 40, 20 to the three drafts, and then sum it up in order to find the final attained index. You may ask why we consider the different drafts. Okay. They reflect the operational life of the ship, that the ship is partly sailing in full draft, partly in partial draft, partly it is empty. And the second thing is that you have not to overestimate some of these drafts, because in some case people said 50-50%. That means I consider only the full draft and maybe the light draft and take 50-50% weight for both. No, this is of course not correct, because the ship will be empty only in very few cases. However, if you consider for the dry cargo ships or for the tankers, for example, even the dry cargo ships, in what cases the ship is sailing in ballast condition and full draft condition, for the tanker ships it is a 50-50 situation. No? For the bulk carriers it is not 50-50 but about. So it depends what kind of trade they have. And something the specialists know is that the attained index for the light draft condition is much higher than for the subdivision condition. That means here you may have some very high attained index, but it is multiplied by 0.2, whereas here the index may be small and smaller than the required index, but this is weighted by 40%. So at the end, the attained index needs to be higher than some required index. And you need not to surpass this requirement by having some good safety level for ballast condition, whereas in the full drop condition, your ship is very unsafe. So we had in the past, I remember this because we did the calculations with Eleftheria during the HARA project. Then we calculated some bulk carriers. The bulk carriers, you have only the full draft and the light draft condition. And at that time, these bulk carriers we calculated, they had an attained index of 0.25, I remember, some small bulk carriers for the full draft condition, 0.25. In the ballast draft condition, they had a very high index, maybe 0.6, 0.7. But not the huge requirement. But in the full draft, it was 0.25. What means that, okay, what means attained index 0.25? Can you understand? That means in a collision, 75% probability that the ship is going to sink. Yeah? That is actually, it's not acceptable. For this reason, later, also in SOLAS 2009, there was a requirement that every index must be at least 90% of the required index. Yeah? So it was, it gives some restriction in the improvement of the rules in order to avoid this kind of surpassing the regulation. No? So regarding the grounding, there was also research in the Course project, but unfortunately it was not possible to develop a probabilistic concept for grounding at that time. At least not a concept that we could implement and calculate the attained index. This was later done in the ENSA 3 study project, and I refer to some publication by Boulian, Zarkonitis, and stuff 2012. There you can read how this is implemented nowadays. At that time, we assumed for the attained index of grounding that it is an index that is about by 10% higher than the attained index for collision. Okay, attained index grounding is attained index of collision plus 0.1, or alternatively by this kind of formula. And in later calculations now by EMSA 3, this assumption proved reasonable. And we have now the evidence that it is. So why we needed to make this assumption? Because now in the cost-benefit analysis that we did for the required index, we need to have also the grounding included in the assessment. That means this was a working assumption at that time that was necessary. And I will explain you why. So now, in order to set up the required index, we did the cost-benefit analysis by studying 2 cruise ships and 2 RoPax ships, large and medium size. These are the sample ships, and we formed design teams consisting of a shipyard that was coordinating respective ships. These were the 4 shipyards, the Maersk, STX Finland, STX France, and Finland Theory. Then some shipping company was in the team, a class society, a flag administration, and university, I mean, SRC and NCAA were participants in these teams. And we did their parametric studies. Actually, the universities did the formal optimization that I showed you before the break. Tomorrow I will show you more about this. But here, the studies were done by the shipyards in a different way. But let me first show you that the sample ships were so that we covered a good range of sizes and also number of people on board. But we didn't have very large ships in the sample. No? So we had big ships, but not very large cruise ships, over 150,000 tonnage, like the Genesis class. For some reason, the industry didn't like these ships to be studied in the Course project. And small ships were not fully exploited. They were also, we had large and medium-sized ships, but not small ships. They came later now in the EDRA-3 study. So what was now here the parameter variation? Because they were so-called risk control options. That means we try to reduce the risk of these ships in terms of collision and grounding, and how this was done by changing of the freeboard, change of breadth, change of subdivision, additional watertight volume above the bulkhead deck, a combination of measures. These were the risk control option measures that we applied, parametrically. Then the attained index was calculated according to Solar Stars 9 and the gold S factor for passenger ships. The cost of design changes was estimated. And I added here, these parametric studies were repeated by formal optimization. That means computerized optimizations, where all these things were changed parametrically and also by making more combinations than done by the shipyards. So here is a checklist, an overview of the risk control options applied for the different ship sizes and what kind of risk control options were studied. Increase of freeboard, increase of depth, change of subdivision, watertight volume on bulkhead deck, and lower vertical center of gravity. So the first of these ships, if you go to more details, was a large cruise ship with 130,000 gross tonnage, post-Panamax ship, with total passenger capacity of 4,200, diesel electric propulsion, and complies with SOLAS 2009, including Safety 24. I think this ship may be the size of Costa Concordia. No? So here is the other particulars of the ship. Maybe of interest, the required index according to 2009 was 0.85 for the ship. So that means you need it by surpass by your attained index 0.85 for the ship to be approved according to SOLAS 2009. So what was studied here? Increase of beam. This was risk control option 1, 1A, 1B, 1C. That means increase of beam by half meter, by 1 meter, by 1.5 meter. Increase of freeboard. This is the option 2A. Increase of freeboard by 0.5 meters, and then increase of draft. Because if you increase the freeboard, then you add some weight, and then you need again you increase the freeboard, but also the draft also increases. You increase displacement. Then the combination of risk control options 1 and 2, 3A, then increase of breadth by 1 meter and freeboard by half meter and so on. So it's some combinations of the other risk control options. It was done this way by the yards. And then this is the outcome of these studies with respect to GM. Of course, when GM increases and goes from 2 meters up to 4 meters, then the attained index increases and comes in this case up to almost 1. As on the top, the index according to gold shows almost 1. Size has a gross tonnage of 63,000. Again, this ship has to comply with SOLAS 2009, including safe return to port. And these are the particulars of the ship. The required index, according to SOLAS 2009, was 0.78. The remainder for the other ships was 0.85. And then we reach some attained indices almost close to 1 in some cases. Okay, but of course with very high attained index, and we cannot see here whether this was cost effective. It was just the result with respect to the attained index. The cost effectiveness comes later. Now here, the options, risk control options, were weight savings and lower vertical center of gravity. That means that the designer started having some lighter structure in the superstructure, and then by that, the center of weight was lowered. By that, GM, of course, was increased, stability increases, attained index increases. Then increase of freeboard by half meter, increase of beam by 1 meter, increase of freeboard and beam, increase freeboard and beam. Okay, some other combinations. This case is also some case that you increase the beam of the ship above water, and that means that when the ship comes after flooding into water, that we have some increased buoyancy, some increased displacement for the part of the ship that is in still water above. And here, by that, this led to some increase of GM, and again, here you see, in some cases, attained index came to 0.95, 0.85, and the requirement was 0.75, as you remember, so it was something around here. Now, the large ROPAC ship with 70,000 tons gross tonnage complies with SOLAS 2009, including safe return to port and Stockholm Agreement. Is a Meyer design. Why this comes now? Large ROPACs here. Okay, these are the dimensions of these large ROPAC ships. The required index according to SOLAS 2009 is 0.84 for the ship. And the risk control options that were applied are listed here. The original version, B3 is the car deck is watertight, entirely watertight. This is control option. Risk control option 1 then is to increase the freeboard by 0.8 meters. Risk control option 2 is increase of the beam by 1.2 or 2 meters into a 3 meter sequence. And so on. These are similar risk control options like before. In some cases here, there was also some transverse division on the trailer deck, on the car deck as a risk control option. That you see here, for example, this kind of, that you subdivide the car deck entirely and then have the ships going into some cells. Of course, this will avoid entirely the water on deck problem. If you would have this, but it disturbs highly the operation of the ship. Maybe some of these studies are theoretical. And the result of this was that the attained index, according to goals at least, goals formulation, came over 0.90. According to SOLAS, it was playing around 0.85, like the requirement. The requirement is here. So we have also these alternative formulations for the attained index according to solar stars 9 and goals led to some differences in the evaluation of the designs. In any case, here is something that is not good at all, because these very high indices were achieved by some GM that is very large, 6.5 meters, 7 meters. That makes the ship very, very stiff. That means when a rolling period is very small and would be not so sea tight. And the medium-size Ropac ship, again Solar Stars 9 ship without here without safe return to port provisions. This is the size, required index 0.79. And again, the risk control options are listed here. Like before, a favored risk control option is to increase the beam of the ship. But here you could also reduce the volume of lower hull, or also subdivide the lower hull. And what came out of that, okay, and then we got a function of GM, okay, then may got very high indices, but also very high GM values. So what are out of this the cost and the benefits? The cost and benefits were determined for each risk control option. The operational costs are adjusted by present value terms by applying a discount rate of 5%. This is important. That means if you do this assessment, you need to do that for the operation of the life cycle of the ship. That means you have to assume that this ship will operate 20 years or 30 years, or 30 years here, we assume. Then you need to make a projection for the cost, operational cost, and fuel cost, especially over the next 30 years. And then you need to project the future cost in present values. Huh? I hope you have done it somewhere in your studies. Huh? What is the present value of the future cost? And this is done by some discount rate of 5%. Properly done. Of course, something I need to tell you is that in these models, we use some cost for fuel that is highly exaggerated. Because at the time we did the project, the projections were that the cost of fuel is about double as much as it is now. So, what means that for the risk control options here, many more will be now cost effective compared to what was assessed during that time. Now, the consequence of the risk control options that the shipyards applied was increased fuel cost that due to increased resistance and increased hotel load, because the vessels generally became more wide because of beam, then this induced some additional resistance and increased fuel. Some increased construction cost, increased harbor cost because of more volume, and loss of revenue in some cases. The benefits were increased capacity, reduced fuel consumption. In some cases, maybe you could get this, and reduce risk of ship loss, and of course, loss of lives. For most risk control options, the fuel costs were by far the most significant cost element. As I said, by today's fuel cost prices, this is not anymore valid. Huh? So this is a nice graph. It shows what? It shows the increase of how much cost an increase of attained index in terms of million US dollars. And this is the increase by, you see, by 0.0246 based on these studies that we did. These are the points for the cost elements. and these are two lines. The first line is, this one is $2 million per 0.01 delta A. That means in order to increase the attained index by 0.01, by 1%, you need to invest $2 million. This line. And here's an assumption that it is 0.5 million US dollars. Depends now how the costs are, and you can see, okay, now say you are with your vessel at attained index of 0.75, and you like to count to 0.85. Then you need to go here because you need to increase by 0.1 and see, according to this model, how much money you need, how much you need to invest.
But these are for new buildings, isn't it? Like,
yeah, new buildings, not conversions. So but it is some existing design that say they have estimated the cost of the ship, how much this would cost if they would change the design of the ship to have a higher index. And the reason why we did that is because later, if based on these attained indices that we calculate now, we set up a requirement, then we needed to see whether this requirement was cost effective or not. And I will tell you why, how you compare now this. Okay, you need to invest some money for this, huh? Maybe 10 million or whatever. Also, this graph is important, is delta risk over the cost. That means how much you need in order to decrease the relative risk by a certain percentage. The relative risk is what? Is the difference to the attained index. 1 minus A is the risk, okay? Say you have, if you have an attained index of 0.8, the risk is 0.2, the risk for the ship to sink. If you like to reduce this 0.2 by 50%, that means to make the risk 0.1 instead of 0.2, by 50%, you needed to invest something, according to this study, in the range of 30 billion, depending, of course, on the vessel type. But in any case, it proves that it is easier to go for a very low attained index to some reasonable index. Say from 0.7, 0.8, it's much easier to go than from 0.8 to 0.9. So it is more cost effective to increase from 0.7 to 8, even though the difference is 0.1 in both cases, but 0.8 to 0.9 is much more expensive. That is what the curve shows. Yeah, for example, this is here. Now, I'd like to say that these cost estimates were done by the shipyards. So it is, there was, I can tell you because I have some different opinions here from the yards and others. There is no way the yards estimate by themselves the cost. There is no way to say, okay, somebody else estimated that and it is not valid because we know that better. At least the yards were forced to do this kind of studies. Life cycle cost and effect on revenue in cooperation with ship owners. That means the ship owners participate also in this study, and they have to agree with the cost. We have a large spread of results. It's clear. It is not easy to say conclusions are straightforward. Change of revenue may cause extreme change. Okay, not in all cases. If you increase the beam, in some cases, you may take some additional row of lane of vehicles, then some additional cargo, but this was not taken into account. We may have some benefit because of increased cargo, given a new design. Fuel cost was by far the most significant cost element in the risk control options. And in most cases, much higher costs than earlier calculated in safety were realized. That means to change this change by 0.1, the safety was assumed that it was less than what was published in the gold spot. So now, how we compare now this with the benefits we have. We have these two criteria that are very important. Also in the facility studies, we find that. The first criterion is the gross cost for averting fatalities, and the second is the net cost for averting fatalities. What is the gross cost for averting fatalities? That is the delta cost, the additional cost you need to invest, divided by delta risk. That means the reduction of the risk by a certain amount. In our case, the delta risk is measured by the PLS, the potential loss of lives. And you relate now the cost to the loss of lives, that a loss of lives we will see have certain value. The net cost of averting fatality is the same, but here you, from the delta cost, you subtract the benefit so that you have a better relationship to the whole thing. There are disputes what is better criterion, whether it's this net CAF or the GCAF. I think this net CAF criterion, most people say it is more valid because here you account also for the economic benefits of risk control options. Whereas in the first case, the economic benefit is not taken into account, but both things are good criteria to evaluate risk control options. Now, the GCAF value, the cost of averting fatality, was estimated in the IMO FSA guidelines back in '96 to be $3 million for every life. In a new study that was done within the goals by DNV, and that took into account the inflation, but also the increase of the living standard of people over almost 20 years. So the cost of life is not the same like was back in '96, because the living standard is now higher. Then this value was re-evaluated, and now it's standing at almost $7.5 billion. That means you evaluate the effectiveness of the risk control options with respect to this new GCAF value. This was, by the way, discussed at IMO in some meeting that we were also participating. It was accepted that this should be the new GCAF value for all studies related to passenger shipping or evaluating the cost of fatalities to take this into account instead of the 3 million value. So based on this, and if we would relate the attained index to the persons on board, then the goals proposal, according to some risk model B, it doesn't matter now here, came to a proposal like this. Of course, there were not enough points here. And these were the original values of vessels, whereas these values also partly produced by formal optimization that I explained before. Then we propose the required index that is coming for the large ships, the level of 95, and this covers also the Genesis class ships that are almost with 9,000 people on board. Some projection. This curve is quite flat, and I think it is reasonable to assume that even for smaller ships, they need to have also a high index, because even if the ship is small, but you cannot say that somebody sailing with a ship carrying 1,000 people should be less safe, say, than somebody sailing with a larger ship where 4,000 people are on board. Respect the probability that the ship sinks and people perish. Of course, in reality, in terms of evacuation, these people will be more happy, easier to evacuate than these people. So this is not the whole truth, because this reflects only the probability of the ship to sink, but not the probability that people are safe, are rescued and are evacuated. This goes opposite way. Okay, there were also other deliberations within the project, and some other proposals that we have this kind of curve. But I think this doesn't add much to the substance. They were spreading around the curves, and I have to tell you that today, after also the EMSA-3 study, the EMSA-3 study actually, surprisingly, not surprisingly, but in certain way surprisingly, all the data were lower than what we calculated in the course project. And finally, I think the curve will be, the accepted curve will be something like that at IMO. We'll see soon, because it is currently discussed at IMO. So the final comments to this study, the level of R index proposed was based on the highest attained indices found to be cost effective for the assembly of ships considered in the course project. The R index was basically attained index calculated according to the Gold's formulation. The Gold's formulation in general gave higher values than the Solar Stars 9 formulation. This we need to say. That means if the level of R would be based on the Solar 2009 index formulation, then the R index would be between 1 and 3% lower than what I have shown you here. In either case, the obtained results indicate the possibility of significant increase of the R index in comparison to the current Solar 2009 standard. And the optimization studies that we performed in Packet 6 of those confirmed the findings of CBA and proved that the level of R index would be even higher than these parametric studies produced by shipyards. Further studies are needed for more ships and different sizes and arrangements to confirm these findings. And this comment here you can say the EMSA-3 study that complemented this by additional case studies surprisingly led to results that were lower than what we achieved in those. And I consider that a backwards development. Instead of going forward, so 3 years later, people designed worse ships than it was 3 years before. No? How you can conclude about it. So my only conclusion, I can tell you, because now here we are, I lecture, is if you don't like to optimize, then you don't optimize, very simply. No? If you like to optimize, you need to have a target to improve something. If you don't like to improve something, then you can stay like that. So here are also some of the experts, because many people contributed to what I presented in the Goals project, also from the industry, many people, and we are thankful to all of them because they provided the expertise for developing this kind of knowledge. That's all for this lecture on risk-based requirement. So I guess you've got some idea what means setting up requirements risk-based, not by statistical analysis. Simply say we have done like in the past, like we have the attained indices of some ships, and then we draw a fitting, and out of that we have a requirement.
And with regards to risk control options, like if you think about the shipyards, it sounds like pretty easy, but for example, increase the risk like it's or like increase draft and but
yeah.
there are lots of limitations because like they already built the these ships according to these limitations, like it go as from a stress.
So of course, yeah. They need
And
to
so
consider that.
it's like it's how many factors can be implemented for how many ships? I don't know, like calculation of the index can vary according to specific. It's very hard to address this problem, but I'm trying to think from the like kind of the end user side, just because they need them and their like design to increase the stability index. There are a lot of limitations, and they need to maybe make a big studies to it.
Okay, if you do the studies manually, then you are lost. Because even the demi stability today you cannot do manually. I mean, you have some software doing the probabilistic approach. That means you need to calculate many scenarios, demi scenarios, 100, maybe 200 scenarios. This is done by computer. But this is not enough today. I mean, today you need to have a synthesis of software where, as I could show you, and tomorrow I will show you more how these parametric models are done. That is the modern way. Then you have parametric models. You produce a parametric model of your ship. Parametric model, what means? It is parameters that change the geometry of the ship around some basic model, okay? Then beam, draft, height, internal compartmentation, as many parameters as you think. Of course, not infinite number, you cannot do that. Huh? But maybe 10, 15, 20 parameters. So if you assign to these parameters 3 values, only 3 values for each parameter, how many combinations you have? How many? 3? 3 powered by 11. If you have 11 parameters and you give 3 power of 11, at least theoretically, that is the design space. And now the question is how you work out, how you explore the design space and you find the optimal combinations, okay? The shipyards doing like this, okay? They see this, but the space is like here, the sky with they don't see that. They don't see that, they don't like to see that. Because the many combinations, so the probabilistic approach is also so that very small changes, whether you say you gain from some damage scenario that you have a survival or not survival, very small changes can assure you that you have a survival case. If you let the computer do that, then you can find much higher indices, of course. That is the key that the shipyards still they don't like to accept. But still, okay, they are not that strict. I think they know. The thing is that the ships will cost a little bit more. And what I said before the break is, are they willing to, the ship owners also to pay a little bit more, and also the passengers to feel safer because you build safer ships. I think inevitably this will come. But they need also some maturity. I mean, these are still new things. Even we are not teaching that. I mean, I'm also teaching this at my university. I mean, it is not time for this. Some people may grasp this and do PhD or so on. Before this can be disseminated and people start applying this and you have a critical mass, then it remains among a very limited number of people. But I think it is room there. We have done it. We have demonstrated that. So maybe after 10 years, more people will easily talk about it. At the moment, the shipyards try to block developments. The same also the ship owners, because they don't like more expensive ships.
IMO sounds like more like a political.
Yeah, sounds it is.
It's like it's.
I want to know the difference between the physical-based project with the safety, the formal safety assessment in the sector project.
The differences.
Yeah, differences.
Okay, there are differences, main differences in the S factor. The S factor is you have in the attained index. Do you understand the S factor? S factor
Yeah, I know.
is the probability, if you have a damage scenario, the probability that the ship survives. Huh? This S factor formulation in SAFETOR is different from that we use in goals.
How is the risk-based here-based?
The risk-based idea in the concept it is the same. But in the goals project, we were more elaborate in the risk modeling. We went deeper. In the SAFETOR project, it was more the framework. In the goals project, we went deeper and developed further the risk model, no? Into details. So in the SAFETOR project, we were more at the top level, and now here we went more to the ground and assumed many probabilities the event risks and whether the ship sinks slowly or and all these are new things that were added. Huh? And finally, as I said, the attained index of goals. If you assess the same ship according to Solar Stars 9 or SAFETOR and goals, then the attained index of goals shows that it is a little bit higher than before. That means the same ship appears safer according to the goals formulation. This has to do how the S factor is, basically how the S factor is. Did you understand? Yeah, the S factor changes and is in the goals project it is related to the critical wave height. That was something developed by Professor Vassalos here. Other questions? No? They know everything? No shipyard participating?
No questions?
No?
Thank you very much once again.
Okay. Thank you for your patience.